Welcome back, my wonderful Allen High School AP and IB students. We're talking about chemical reactions. We've covered how to write net ionics. What I want to move into now are the types of reactions that you will have to recognize, predict, and or interpret experimental data involving these types of reactions. So let's dive into double replacement reactions, sometimes called double displacement. I like replacement. I think it's just what I've become used to. And what a double replacement is like is, I know Ms. Marusik likes to call this a wife swap. Or you can call it exchanging dance partners. All right, so how you're going to recognize this is we're going to have two reactions that are compounds. It could be an acid, a base, or an ionic compound. But you're not going to have an element as a reactant. So the key is there's going to be two of them. So if I had AB, or AD, I guess, plus BE, they're going to trade dance partners. So if this is me, and this is my husband, and this is Denzel's wife, and this is Denzel, you know, of course what's going to happen the minute Denzel dances near me, he's going to steal me from my husband, but that won't be too bad because that leaves my husband with Denzel's wife, and I bet she's a lovely dancer as well. And that's how we're going to track it. Now, we have to have a driving force for these to occur, and for our driving force, we need to form a solid, a gas, or water. Really, a liquid is what we're after. A molecular substance would be the formation. This would be our driving force that would cause this reaction to occur. And this is key. Double replacements are never a redox. Never. And that's because we're going to make sure that our oxidation numbers are always the same. So let's take a look at this reaction. Solutions of silver nitrate. So silver is part of your staircase. It's always +1. Nitrate's -1. Sodium's +1. Chromate's -2. Now let's draw those out then. So I'm going to do the sodium chromate first just because I started writing that. So we have sodium chromate. Because it said solutions of, I know that means it's aqueous, plus silver nitrate. It's lovely stuff. It'll turn your skin a lovely color of brown for a few days. Aqueous. All right. Now, we're going to have a reaction. It's helpful to write these charges down because then when you do the reaction, the positives are going to dance with the opposite negatives. So cations have to go with anions. So that means silver is going to dance with chromate. Well, if silver's +1 and chromate's -2, I need two silvers to dance with chromate. And that leaves sodium to dance with nitrate. Now, you may be told that a precipitate forms, or you may have done this experiment and seen the precipitate. Well, if you memorize just a couple of rules, and one of them is that all group 1 salts are soluble without exception, it's clear that that's our aqueous component. That means this is the solid that provided the driving force. So that's my complete formula. Now what I'm going to do, I'm going to drop my states at this point. I'm going to dissociate this into ions. Notice that that 2 becomes a count because the sodium ions now kind of swim away from one another. They're not bonded to that chromate ion anymore. So I have 2 sodiums, I have 1 chromate. So that's like saying the sodium twins drove to the party with chromate. Now that silver nitrate was also a solution. So I have silver plus nitrate. That's dissociated. And notice, and I really should have balanced this, I needed a 2 there and a 2 there. So I'm going to go ahead and balance that. Now that I am not going to dissociate the silver chromate because it's a solid. We do not dissociate solids and weak acids or water. And then I'm going to get 2 sodium ions plus 2 nitrate ions. Now let's take a look. What is the good gossip at the party? The good gossip at the party is that silver ion reacted with the chromate ion to make silver chromate. And you know what? Sodium came to the party, had a good time, but went home alone with no new boyfriends. And nitrate went to the party and went home alone with no new boyfriends. All right. Now, when you do these, what would be evidence of a chemical reaction? Well, first off, we would see a precipitate form. So that solid means we see a precipitate. Plus, we're going to see a change in color. When you have transition metals that have an incomplete D sublevel, they're likely to confer color on the compound. Incomplete, D sublevels. So that chromium's going to give it a color. Okay, and sodium chromate's going to be, very likely to be different from silver chromate, plus that's now going to be a colored precipitate. I'm going to do this next one quickly. I have sulfuric acid, aqueous, acids by definition are aqueous, plus barium acetate, C2H3O2. That's said solution of, so that's aqueous. All right, since sulfuric acid is made of +1 H and -2 sulfate and +2 barium and -1 acetate, I'm going to get 2 acetic acids. Let me erase that, make sure I get that correct for you. C2H3O2 acid. Now, I'm going to get then the positive barium will go with the negative sulfate, so I'm going to get barium sulfate. Right? Now, this is not a group 1, it's not a group 2, it's not a group 1 metal, it's not nitrate or acetate or chlorate. Those are your common soluble substances, so that's likely to be a solid. Okay? And since it's not a transition metal, it's likely to be a white solid. So white solids or white precipitates typically would form a colorless solution. Okay? Now, sulfuric acid, only the first H is strong, so I'm going to break that into H plus HSO4 minus. This is aqueous, so I have barium 2 plus 2 acetates. Acetic acid is weak, so I'm going to keep it together. And then I have my solid barium sulfate. And there are no spectator ions in this reaction. So my net ionic is identical to my complete ionic. So this is how I would write the net ionic for this reaction. The biggest evidence of a chemical change here is when you are mixing 2 aqueous solutions, when you get a solid, we call that a precipitate. So we'd see a white precipitate form in this chemical reaction. You may see the pH go up a little bit as well because this is a weak acid, but it really depends on what is in excess and what is limiting. Okay, so that's our double replacement reactions. In our next videos, we will continue our discussion of classifications. Until then, this is your beloved chemistry teacher signing off.